Okay. So is this one where you have it, do you have like that filled out? No. Okay, so go ahead and fill those out right quick. Crisscross, crisscross away. They're fun. So go ahead and fill in that. Trying to shake off that Thanksgiving break that we all enjoyed. Very good. So now it's not too bad if you're given the component ions. And I guess I want to emphasize that if you have the name, okay, so say you have potassium chloride and you're supposed to write the formula. And I saw a lot of you doing this on your homework. Sometimes above the potassium you'd write +1 and above the chloride you would write -1. Okay, so be able to do that. So let's just go around the room right quick. And the catch here is, do we use Roman numerals or not? So we'll start back there with you, Shelby. So that Ca +2, what's the name of that? Is it calcium or calcium 2? Calcium. It is just calcium. Very good. Cool. What about K+? It's just potassium, exactly. Those are both over here. Perfect. 1A and 2A, or 2A and 1A. How about Quade? Barium +2. Do we use Roman numerals or not?
Yeah.
Why?
Wait, never mind, it's in there. No.
Nope.
It's in the second one.
Nope, because it's in the second column. Perfect. No Roman numerals. And see, this is where I run into students on your test. You'll maybe get in a hurry. Okay, find these things on the periodic table. Okay, so what do you think about PB +2? Do we use Roman numerals, Shelby? So it's, do you know what PB is? Lead. Lead. It's lead 2. Very good. We use Roman numerals. And then what do you think?
Lead 4.
Lead 4. Perfect. Back to you, Shelby. Sodium? Use Roman numerals? No. It's 1A. How about aluminum? No, you're very correct. And pretty much all those guys under aluminum, no, don't use Roman numerals. Cool. This is aluminum. How about cadmium, Quade?
Yeah.
Why?
It's not in the second column.
Well, we don't use Roman numerals. And if you find on the periodic table, what's above cadmium?
I can find it, so.
Oh, yeah. Yeah, above cadmium is zinc, and then to its left is silver. And clustered together here, annoying as it is, are the only 3 that you don't use Roman numerals for. But if you find them, these actually are +2, and this is always a +1. So if that helps. I know all these silly little things. So cadmium, no Roman numerals. Shelby, how about magnesium? No, just magnesium. And I have no idea why that's up there, but Joshua, what's the name of that? Do you know? NH4 plus 1? Ammonium. Very good. Ammonium, yes. I don't know why that's on that slide. Okay, Shelby, Fe. Roman numerals or no Roman numerals? Yes. So it'll be iron 2, and I'll put iron 3 there. That brings us to zinc. Roman numerals or no Roman numerals? No. Just zinc. Very good. Copper, Quade?
Yeah.
Yes. So copper 2, copper 1. Nickel, Shelby? Yes. Yes, we do. So nickel 2, nickel 3. Silver, Joshua? Nope. Just plain old silver. These are the most annoying. And you guys did well on your homework. So what's the name of this one, Hg2+.
Mercury 1, or Mercury 2.
It is mercury 2, very good. And then, what do you think for this one?
Mercury 1.
Mercury 1, polyatomic cation. They are annoying. I grant you that. Okay. So, hey, this isn't too bad. How about Quaid? What's the name of the first one? What is it? Oxide. Oxide. Very good. The name of the next one?
Nitrite or nitrate?
There's no oxygen, so it has to end in IDE.
Oh, okay.
So nitride. I tried nitride. Yep, nitride. These are all IDEs.
Oh.
What about this one?
Sulfide.
Sulfide. Very good.
Chloride.
Chloride. Great. Not hydrogen, it's hydride. Very good. Hydride. You got it. Next one, Quaid.
Bromide.
Bromide. Sorry.
Phosphide.
Phosphide.
Fluoride.
Fluoride.
Iodide.
Iodide. Yep. Very good. Let's see what else I have next. Oh, yeah. So near the end, we have these. Okay. Okay. Let's see. How do I want to do this? I know. We'll still go around the room. You guys are doing great. I'm going to call this one A, B, C, D, and E. Okay, so Grant, what do you think is A? Which name matches up with A? You got the hardest one because I'm going to cross it off once you figure it out. It's got chromium in it. Look, how good of a guesser are you?
Is it
No?
No.
I'll give you a hint. It's got,
Oh, it's dichromate.
it is dichromate. Very good. Okay, B, Quaid. Hydrogen carbonate. Very good. C, Shelby.
Permanganate.
Permanganate. It's a beautiful purple looking thing. Makes you want to drink it.
Carbonate.
Carbonate for D. And then back to you, Shelby.
Chromate.
Chromate. Okay. So I kind of wanted to do this just to kind of make sure we're all on the same page. We're actually going to leave this material. Part 6, we did it in lab, and that's about it. But there's still, remember I showed you that, not Jenga, the Mahjong, where the tiles and stuff like that. Somehow you got to get these down. Okay. Then we have another set. Ooh. Is that the same set? Oh, here's the names. Okay. Now we go on to this set, and I'll call them, like I did before, A, B, C, D, E. And I think we're ready for you, Shelby. What's A?
Sulfide.
It is sulfide. Very good. What is B, Grant?
Is it sulfite?
Nope.
Sulfate?
It is sulfate. Very good. The sulfite has a little less oxygen. So it's down here. I know it's annoying, but this is sulfate and this is sulfite. So how about the next one? Hydrogen sulfite. Which one is that one?
Oh.
Quaid.
D. Wait, no. D.
Final answer?
Yeah.
E. It is E. Very good. Yep. Annoying, annoying. Shelby, hydrogen sulfate.
C.
It is C. Seems like we're missing one up there. We're missing sulfite, right? Oh, no, sulfite. Ugh. No, I missed it. So which one's sulfite?
D.
It is D. Very good. Cool. You got it. Okay. I think this might be the last set. And we're back to you, Shelby. So I'll try not to miss one this time. A, B, C, and D. How about phosphide? It is C. Very good. How about phosphate? It is A. Very good. Quaid, how about hydrogen phosphate?
B.
Nope.
Then D.
What's that?
Then B.
Did you say D or B?
I said B, but it's not B.
Oh, okay. It is D. Hydrogen phosphate. And then the last one, Shelby. It is B. Okay. So every semester, my husband teaches this class too, and every semester we get together and we're like, I know they're going to kick butt on this on the test. And so don't let me down. Okay, so you kind of know what you need to study. Okay. Right. Okay, I think that kind of does it. This slide, I just wanted to remind you that if you, and you will need to, be given these blue lists right over here, if you need to give the name of the compound, feel free to break it out into its component ions. Read it cation to anion. Look for something that's positively charged and something that's negatively charged. And you're going to have to know your polyatomic ions. So like for instance, this one, it looks Greek. NH4NO3, you're like, what the heck? Why didn't I put those nitrogens together, right? But if you read it from left to right, hopefully you're looking for a cation, and then you're looking for an anion. Okay, so kind of go with that. Okay, that might be about it. But I did write something on the last slide. Oh, see, there it goes. So we've had a few opportunities for extra credit points, and this is actually another opportunity. Not only, though, would this give you 10 extra credit points. Now, your extra credit points only go towards missed assignment points. And sometimes students say, well, I haven't missed anything for my assignments. And so where do these points go? And I'm like, I don't know. You can't sell them. They're non-transferable. I don't have a place to put them. But what I started to say is not only are they extra credit, but they will help you on the test. I would actually study for it like it's the test and then go do it. So, okay. Now we're on to part 7. Oh, I forgot to bring my... I'm going to go back and get them because my little structures. So we're switching gears. Remember up here I put molecular compounds and ionic compounds, and you kind of need to know some descriptive things about those two types of compounds. Okay, so we're switching gears back to covalent compounds from ionic compounds. Okay. So covalent compounds are stuck together, the atoms are stuck together by covalent bonds. And the thing about covalent bonds instead of ionic bonds is electrons are shared. Okay, so these are like some deja vu slides. You're like, we already talked about that, okay? And you're right. So covalent chemical bond, a chemical bond that's covalent, we have a pair of electrons that are being shared, okay? And if all of the things, chemical bonds holding the atoms together are covalent bonds where electrons are shared, then the compound is a molecular compound or a covalent compound. Those are synonyms. Again, we talked about this. I had to double check. I'm like, did we talk about this? Because sometimes I get my intro and you guys mixed up. We talked about electronegativities. We said electronegativity increases from left to right and increases going up. Electronegativity looks like this. But I finally moved the arrow because I kind of think of them meeting. Okay, electronegativity increases. And we use that funny looking X. It's the Greek letter chi for electronegativities. Electronegativities are like a tug of war for the electrons that are connecting atom A and atom B together. You can only talk about electronegativity if you're in a bonding situation. So we said that the nonmetals tend to have high electronegativities because they want to form anions. And the metals tend to have low electronegativities. They give up electrons, form cations. And these are the Pauling values. Minus Pauling got a Nobel Prize, I think, for coming up with this. Okay, so these are, if you have these atoms in a bonding situation, this is their tug of war effort to get the electrons. Okay. And this is deja vu too. We already talked about all this stuff. Because in that tug of war, what we do, and I don't know if I necessarily need to do it again, but here we have atom A, and you have a chi A, or electronegativity for that A, and it's bonded to atom B, electronegativity for that. Hope this is ringing some bells. You calculate the delta chi, the electronegativity difference, simply by taking the absolute value of the differences. Okay, remember that? And we said if your delta chi, if your electronegativity difference is greater than or equal to about 1.7, then the guy with the higher electronegativity actually will grab onto the electron and leave the other guy A behind. So electron will be transferred. This will become negatively charged. This will become positively charged. Okay, and then you get an ionic bond. But let's just say you grab two nonmetals, and those are going to be your atom A and your atom B. Bottom line is you're going to be less than 1.7. So remember over here, when I had my kind of list of things going with two types of compounds, with regard to the molecular compounds, I said they are all nonmetals. So here we have the nonmetals that are emphasized. So if you kind of see the invisible jag separating the metals from the nonmetals. Okay. So now, as we start to share electrons, I know it says double dip, but I almost think joint custody of the electrons. So, for instance, a water molecule, okay, we have 3 atoms that we're going to stick together, okay? Our water molecule, the Lewis structure, and we'll talk more about what Lewis structures look like, but our Lewis structure looks sort of like this, okay? Where that line that I'm drawing, that actually is a covalent bond. Covalent chemical bond. Okay, now I'm not quite done. One of the things we're going to talk about today is kind of an interesting little thing that happens with molecules. I'm going to take my oxygen and I'm going to put those dots. Each dot is an electron, and they come in pairs. So actually there I have two pairs of lone pair electrons. Okay. So I mention all this, and you guys know about the whole octet thing. So electrons are transferred so that metals and nonmetals have a complete octet. And electrons, in this case, are being shared, so the atoms can have a complete octet. So you can get this kind of Venn diagram going on. So I'll pick on the oxygen. If I draw a Venn diagram around all of the electrons that oxygen has custody, it has sole custody of these 4 electrons, and it has joint custody of these 4 electrons. And actually, I have a slide coming up that says anytime you see a dash like that, it's a covalent bond. Think of 2 electrons there. So I have 2, 4, 6, 8. So there's my octet around oxygen. So I said joint custody. So these 2 electrons right here are shared jointly by the oxygen and the hydrogen. So let me go ahead and draw a little Venn circle around my hydrogens. Okay, they don't have an octet, but they have what? A duet. 2 electrons. And if you look above neon, okay, of course, helium is a rare gas, and it has 2 electrons. So it does have a rare gas configuration, it's just not an octet. So that's what we mean by sharing electrons. So it's all about octet, octet, octet. Well, sort of. We have we have some situations where that's not the case. The element boron, which is right on the jag, right? Okay, boron actually doesn't want 8, it wants 6. So in its final structure, you're going to see it have joint custody or full possession of 6 electrons. The other thing is hydrogen. Okay, oops, and it's coming up. The other thing, and how do I say this? This will kind of shake itself out as we go on talking about Lewis structures of covalent or molecular compounds. But if you have an atom that is period 3 or greater, okay, so find period 3, and that's like way up there at the top of the periodic table. So basically we have quite a few potential exceptions below that. Now an expanded valence, let me just go ahead and tell you. Octet, of course, is 8. So rare gas, we think of 8 electrons, right? Your expanded valences, they come in forms of, I've seen them in 10 electrons and 12 electrons. So it's possible, you might even have some homework where you're going to see the final structure of a molecule or a polyatomic ion, and you're going to say, that must be an expanded valence, because I don't see 8, I see 10, or that's expanded valence, I see 12. Okay. So a simple view of that dash, that covalent bond. So think of it like this. Now, we talked about how electrons are configured. And we said electrons hang out in these boxes we call orbitals. That's an atomic orbital. Well, here's the deal. And this is, I think, I've thought about this, hasn't been all that long. There's my atom A, there's my atom B, and they're going to make a covalent bond. Okay, that could be the nucleus of the atom. That could be the non-valence electrons, okay, or the inner electrons. And so what happens is atom A sends out, I'll make it look like it. Remember we said that p-type orbitals kind of have this lobe sort of thing going on? They have that shape. I'm going to have A send out one of its atomic orbitals, and I'm going to have B send out, I'll change colors, an atomic orbital. And they don't have to be a p-type, although this definitely looks like p, that dumbbell sort of thing. It could be spherical, s-type. Okay, and actually 2 atomic orbitals overlap and create something that's called a bond orbital. So right there, I'm running out of colors. Right there, okay, that is my bond orbital. It's a region in space, okay? And the rules of that orbital, now it's a bond orbital, that's the overlap of 2 atomic orbitals. The rules of that new orbital are the same rules we talked about before. 2 electrons, in this case it has to have 2 electrons. That's kind of the dash between the 2 atoms. And this talks about the degree of overlap. Actually, there's different amounts of strength, bond strength, associated with the atoms that are being the atomic orbitals that are being overlapped. So that bond orbital needs to have 2 electrons, no more, no less, and the 2 electrons have to have opposite spins. Okay, I think we call that, I get my Hund's rule and Pauli's exclusion principle mixed up. Hund's rule is they need to spread out, and Pauli's exclusion principle is if you're going to put 2 in a box, they have to have opposite spins. So if we go back to the water molecule, the quick draw that Lewis structure. Looks like here's my oxygen, covalent bond. Remember, there's 2 electrons, covalent bond, 2 electrons. And oxygen has actually 4 electrons paired up. So two lone pairs of electrons. But hydrogen, how do I say this? Hydrogen is atomic number 1. It has 1 electron. So that's to say, of these 2 electrons that are there, 2 electrons every time you see a dash. Only one of them came from hydrogen. The other one came from oxygen. So it's like a mixed bag. I'll do that for hydrogen, and I'll do that for oxygen. Okay, it doesn't have to be that way. Sometimes both electrons that are in that bonding orbital come from a single atom. Here it's 1 electron from each. So this will make more sense later, but in our Lewis structures of water, I drew an oxygen dash hydrogen, oxygen dash hydrogen. Those are what we call single bonds. And we're going to look at some structures here. For instance, if I had a carbon atom and a carbon atom, that's a single bond. So 2 electrons? Well, a triple bond on your Lewis structure, double bond, excuse me, will look like this. And I bet you've seen them before. Carbon dash dash carbon. So that is a double bond. So 4 electrons? 'Tis true. And last but not least, a triple bond looks like this. Carbon dash 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 carbon. How many electrons are there? 6. Yep, 6 electrons, 2 for each dash. Exactly. Single, double, triple. Just like in baseball. Okay. So a covalent chemical bond is electrons are shared. A pair of electrons are shared to create that dash. Now, we have 2 types of covalent bonds. We have sigma covalent bonds and we have pi covalent bonds. Sigma and pi. Sigma is that Greek letter with a circle with a little dash. That's sigma. Okay? That's like the lowercase, because the other sigma is that E-looking thing where you sum. Okay? Anyway. So sigma bond is called the primary bond, and I like that name for it because I kind of say sigma bonds are the first to arrive. Sigma, they're primary. Okay? So in the case of a single bond, it's a sigma bond. Okay? It is totally a sigma bond. Now this is why I went and got my little models here. Okay? So this is C2H6. So I have 2 carbons, they're the black balls, and then I have 3 white balls over here for hydrogens and 3 white balls over here for hydrogens. So C2H6. Now, those gray regions are where a pair of electrons are hanging out. Okay? Yeah. Nope, they are the electrons that are in the covalent bond. They're in that bond orbital, that overlap of 2 carbon atomic orbitals, bond orbital. Okay? Carbon-hydrogen atomic orbitals overlap, and here's the 2 electrons creating that sigma bond. Okay, sigma bond, sigma bond. So this says where are the electrons? Because they've got to be somewhere. I mean, matter is so cool. Molecules are so cool. This is how we're all stuck together. Okay, either with covalent or ionic chemical bonds. Okay, so where are they going to be? They're going to be, like this says, kind of connecting the nuclei. Now, if you have the main course, then you can have dessert. So sigma is primary, pi is secondary. Pi is secondary. Do all atoms or all atoms bonded together with a pi covalent bond? No, it's secondary. You don't need dessert. Yep. Unless you're my grandmother, and we used to, she's passed away several years now, lots of years, but when we went to Country Kitchen, she'd always want to look at the pie first, and she'd just get her pie. She'd start with secondary bonds. Okay, so, but you can only have one primary bond, but you can have multiple secondary bonds. You can only have one sigma, but you can have multiple pies, which my grandmother would love. Okay? So if you have a double bond, the first to arrive is the sigma. Sorry, yeah, double bond. Okay, the first to arrive is the sigma. That's a sigma. And then the second to arrive is the pi. That's how I think of my double bond. If you have a triple bond, 6 electrons, we have sigma, pi, pi. So the first to arrive is sigma, and it doesn't have to be the top one. I don't know.
okay? But these other two are pi bonds.
Okay, but electrons are being shared also. So you're like, all right, where are those electrons, Mrs. Snipes? Well, those electrons are here. Okay, so this is C2H6, and this is C2, okay, oops, C2H4, 1, 2, 3, 4, C2H4. So of course you see your sigma, 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 sigma connecting the carbons and the hydrogens. You see the sigma there connecting the two carbons. Okay, and the deal with this purple and this pink is they go together. It's kind of like the little hot dog sort of thing. It's sandwiched. Actually, there's a pair of electrons that occupy this region, okay, around the sigma bond. Okay. Well, that's a double bond, so here we have sigma pi. That's a double bond. What does a triple bond look like? This is what a triple bond looks like. Okay, so once you get past the whole color thing, if you focus on the atoms, we have carbon, carbon, this is C2H2. So carbon, carbon, sigma bond, carbon, hydrogen, sigma, carbon, carbon, hydrogen, sigma, okay? So here, again, we take a pair to make the pi and a pair to make the pi. Now, one of the things we can talk about with molecules is what is the shape of the molecule. And actually this thing, if you take away kind of the buzz of the bond electrons, the pi bond electrons, doesn't it look like a hot dog that's linear? This thing's linear, the molecule's linear. And this one actually has a couple of trigonal planar features going on. Okay, and this is has a couple of what we call tetrahedral regions. One more thing, well there's a lot of things, but this, does it seem like I can go ahead and just twist away? Okay, single bonds are great at that. Just twist. That actually has applications when it goes to do things with other molecules, to interact with stuff. Okay, does it look like I can twist this one? Not without breaking it. There's no free motion around a double bond, let alone a triple bond. One of the things we're going to talk about is bond strength and bond length. Does this one look really strong? Triple bond, oh yeah, okay. This is the weakest, okay. This one, this triple bond is actually the shortest, okay. And these are the longest bond lengths, the single bonds, if they're between carbon, or between atoms of the same type. Okay, so sigma, primary, pi, secondary. So when we were talking about we have talked about how you can look at the periodic table and knock out the number of valence electrons. Remember electrons that are in the highest n. Okay, that's from their group number. Now this concept of the valence of an atom that is in a molecule or in a bonding situation, the expected valence of an atom, it's a little bit different than valence electrons. Okay? The valence of an atom actually is, let me highlight what I think is important. Well, what I think is important is in the parentheses right there. The expected valence of an atom is the number of times you want it to, I'll say, reach out. Reach out. And when I say reach out, it's going to reach out, because we're talking about some other sort of thing, it's going to reach out forming the primary and the secondary bonds. Reach out forming the sigma and the pi bonds. How many times is it going to reach out? Well, it's going to reach out, or its expected valence is 8 minus the group number. So if we pick on carbon, actually, it's the next slide, isn't it? Oh. The expected valence for hydrogen is 1. Now this will have applications in your drawing your structures for Thursday. So hydrogen only wants to reach out once. Does this make sense? If it's going to reach out, it can't be a pi bond, right? It's going to have to be a sigma bond, the primary bond. So you're going to only see the hydrogen bond once. And boron, it's going to reach out 3 times. I don't do much with boron. So this is actually, if you want to put at the top of this, this is the number of sigma and pi bonds. the expected valence, not the same thing as valence electrons. The carbon's right, but if you start going number of valence electrons for nitrogen, that's a 5A. Okay, it's not 3. Okay, so over here I have I'll write the group numbers. So this is 4, 5, 6, and 7. So if you take the group number, or 8 minus the group number, then you get these guys over here. And hydrogen only wants to reach out once, and boron 3 times. Seems like did we talk about these? These aren't Lewis structures. Well, they kind of are. They're like Lewis electron dot structures, where the symbol for the element is the nucleus and all the electrons that are non-valence electrons. So carbon's 4A, you see 4 valence electrons. Nitrogen 5 valence electrons. 6, 7 valence electrons. Of course, neon is a rare gas, 8A, 8 valence electrons. But doesn't that kind of creep you out? Let's do it again. Goes back and forth. Anyway, I kind of think of, I know it's silly, but we have our son. How old is Craig? 20. I think he's turning, his birthday's next week. I think he's going to be 26. Yeah, because he's born in 2000. No? Would that be right? Yeah, no. He's born in 90. Yeah, in 1990. Oh, time flies. You just wait. 1990. So he's 26. He'll be 26. Anyway, I think of him as little cars, and that's what those arrows remind me of. It's like they're parking cars in a garage that has 4 sides, and you can put 2 cars in each garage. I don't know. Anyway, there you go. There's 4. And of course, nitrogen only has places for 3. Oops. Oxygen has places for 2. Fluorine has places for 1. And neon's full. Okay. So you kind of have, that kind of shows you how they might reach out and shake hands with regard to forming sigma or pi bonds. Okay. Well, I think that's a good place to stop. Okay? And we'll pick up here and go on to part 8. So, yeah, there's homework at the end of this part if it helps you at all. Let's see. This is what I'm going to say for that. Blah, 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 blah. Oh, there it goes. Oh, come back. Are you serious? Anyway, that homework is going to be due on December 5th. If you just want to say December 5th at the end of part 7. Because I want to get the lab under your belt. In fact, that homework might be the one I have you guys do for your lab credit. That sounds like a good use of. So that's all I have today.
So the purple and the pink, those are the pi bonds.
Yes, and they got to go. You have to have both.
Okay.
A purple and a pink to make the pi bond.
Okay, and then the rest of the ones are sigma. Okay.
Yep, the grays
That's
are
really
sigma.
cool.
Yeah, I think so too. This is benzene. It's missing a hydrogen, but this is C6H6. So that's really cool.
I don't function well when I don't eat.
What's that?
So I don't function well when I don't eat.
Uh-oh. I can relate. I get real crabby when I don't eat, so watch out.
See you Wednesday.
Sounds good.
You could be driving trains.